so we'll continue on with, again, more examples of things that we can do with integrals. And so the next one is about capacitors. And so with capacitor, one of the things we remember from back when we talked about it with derivatives is that we can relate capacitors by the function, by this relationship that says that our current, I of t, is the capacitance times the derivative of voltage with respect to time. So if we rearrange that, similarly to what we've done with other expressions, we can get an expression for voltage in terms of capacitance, or at least in terms of current, that's used for capacitance. So let's work through that. So we can move dt to the other side, and then integrate both sides. And if we take, remember, we can do this with respect to time. Those are our limits. The antiderivative of c dv, I can bring the c out front, or I could have left it in there and used it there, but I'm going to bring it out front because I think it's going to help me in a minute. Antiderivative then of just the constant is v, evaluated from 0 to t, so then it's whatever v of t is minus v of 0. We'll rearrange things. So we'll just divide both sides by c, so we get 1 over c out front. We can bring that out of the parentheses, and then we can move the v0 to the other side, and I called it v sub 0 right there. So my expression for voltage is 1 over c times the integration of the current plus whatever my initial voltage is. So now we can use that to work out some examples. So for this particular example, we've got I of t is 0.024 e to the negative 40 times t, and that's a current, so it's measured in amps. And we've got capacitance is 3 microfarads. So remember, that is 3 times 10 to the minus 6 farads. We'll need to plug that in just a minute. So we want to know what is the voltage. Okay, so we start with our generic expression. I flipped it around so that we have v of t on the left. And then we put in the values that we know. We've got 10 to the minus 6 farads here. We've got our function there. We can assume that the initial voltage is 0. And then we need to do the antiderivative. When we do the antiderivative, if it's e raised to a constant times a power, we still have e to that constant power, but we have to divide by what that power is, so in this case negative 40. So when we simplify this expression, so we put in a value of t, you put in a value of 0. Remember, that's going to go to 1. It doesn't go away, it's still there. And we've got minus a negative 40 there, so it's actually going to be positive. So what we end up with for v of t, I'm going to go ahead and pull all these coefficients out front of 0.024, 3 times 10 to the minus 6 is still there, and the 40. And we actually end up with that expression, negative e to the negative 40t, and this is just plus 1 over here. So I should simplify that term on the left, or my coefficient term, and rewrite it a little bit easier to deal with. So when I do that, I end up with this expression that just says that the voltage is equal to 200 times 1 minus e to the 40t. So all that expression turned out to just be 200, made things nice and easy to figure out. And of course the units on these are going to be volts, because it is a voltage. So yeah, we can see as time goes on, it kind of dissipates. Correction, it doesn't dissipate. This term goes to 0, so it actually gets closer and closer for being that 200 value. So if we were to sketch what that would kind of look like, it would look something like at time 0, it's 0, and eventually, with it being an upside exponential function, the limit is 200. Which makes much more sense for a capacitor, because the idea behind a capacitor is as we load charge into it, it stores an amount, but it's going to have a maximum amount. So the maximum capacitance must be somewhere around 200. So the key things we've learned so far is that we can relate, for a capacitor, we can relate the capacitance and the current to voltage using this function. And then we just applied it as an example there. The next concept we want to work with is this idea of stored energy. And another thing we remember from back of our previous discussions of power. So we want to know about energy. We're trying to learn about that. What we remember, hopefully, or look back up, is that we remember that power is actually the derivative of energy, because power is how much energy is used over time. But we don't know how to get power. We can't get power directly from that unless we remember another expression, which is this. We remember also an expression from using the chain rule was that we could get that power is current times voltage, and that comes from this idea of using the chain rule, which noted that current is the change in charge with respect to time, and voltage is the change in work with respect to charge. So when we multiplied those two together, these canceled, and we were left with work over power. So if we go with that idea of expression, then we can get to an idea of work from current and voltage. So we set those two expressions equal to each other. dW dt is current times voltage. We'll split the dt to the other, and then integrate both sides with respect to t. Or rather on the interval 0 to t. And if we split those over, do the integration, and then we know we can take this expression and move it over there, we end up with another similar expression that tells us that the stored energy, or W, over time is the integral from 0 to t of the current times the voltage with respect to time. And so now we can take those and we have expressions that deal with each of those things and calculate them out. So from our example, we were given that I of t was 0.024 e to the negative 40t. We used that to find that the voltage was 200 times 1 minus e to the negative 40t volts. And so now we can use those expressions to get what the energy is. So we end up with this expression, I of t, V of t, our initial work, our initial energy. And now there's a few different ways to do this. One would be we want to pull out the coefficients first anyway. There's two different ways to go about the next part, which is one, you can recognize that we could use a chain rule to kind of see what's going on. What I'm actually going to do is just multiply the thing out. So if I just multiply the coefficients and bring those out front, I get, that's 4.8. I get negative 40 times 1 gives me e to the negative 40t. When I multiply these two together, remember I add the exponent, so I get negative 80t. And again, these are easy to integrate. So again, key points that we did there. We got the antiderivative, so we just had that and divided it by those. We plug in these values of 0 to t. So to do that, I'm going to go ahead and take out this factor of 80 from here, move it out front with the rest of it. I've lost my extra factor on here. So that becomes negative 2, if I multiply this by 80, because I divided everything by 80, becomes 2 e to the negative 40t. That one, negative is positive, so it becomes e plus e to the negative 80t. Now I've got to add in from 0 to t. So let's evaluate at the limits. So again, as you plug in t, simplify that lead coefficient, just comes 0.06. Plug in t, we get that part of the expression. Plug in 0, we're going to end up with 1 and 1. So negative 2 plus 1 is negative 1. It's going to end up minus, so we're actually going to end up adding in there. So we should end up with an expression that looks something like this. Now the interesting thing is we get negative 2 e to the negative 40t, we get e to the negative 80t, and we get a plus 1 there. The interesting is if we rearrange that, it actually looks like a perfect square. So what it actually looks like, if we rewrote this, is 1 minus e to the negative 40t, that quantity squared. Where does that come from? Well, think about it if we went back the other way. If we squared this out, we'd get that squared. If we squared that out, we'd get plus e to the negative 80t. And if we think the middle term would be negative 2 plus that. And so that's one way to get there by just doing the multiplying it out. The other way to look at that is we could have gotten there through using what they call the chain rule. So I'm going to actually slide over here to the left and show you what that looks like. Okay, and so the magic of things is I just said let's just use this chain rule as if that automatically meant something to you. Well, the idea is if you look at all the expressions we have on our reference pages, they talk about using the integral of u du, or something with respect to u du. And we've always took that to mean we'll just put t or x in terms of u and replace that. Well, what if u is actually an expression? What if we let 1 minus e to the negative 40 t be u? Well, then du is, the derivative of u is, the derivative of 1 is 0. The derivative of negative 40 e to the negative 40t is 40 e to the negative 40t dt. So if I can make something that looks like this out of this expression, then I can just integrate that whole statement of this. So let's rearrange this. I know it looks like if I just pull everything out, I get 4.8 integrated from 0 to t e to the negative 40t times 1 minus e to the negative 40t dt. So I get that expression. Well, what I need to have, this is u, so for the du I need to have 40 e to the negative t. Well, then I'll just make it be that. And just remember, anything I do inside I have to counterbalance by doing it on the outside. So this can be written the same as 4.8 divided by 40. And I'm going to change the order of things just so that it looks like what I'm talking about. Then if I've got this, notice this is u, and this is du. 40 e to the negative 40t. And again, that just comes from taking, I got a 40 there, so I had to divide by a 40 out there to make that work. Okay, so if that's the case, now, using this rule, I can just say it's this expression, raise the power on it, and divide by the new power. So this is Wt and keep my 4.8 over 40, but it ends up being 1 plus e to the, or 1, I'm sorry, it's 1 minus e to the negative 40t squared, that's my u. I have to divide that whole thing by 2. And I would still evaluate from 0 to t, and I left off my plus w0, those sorts of things. But the key point is I've got this expression in the middle, which will come out a little bit more simple. And actually, if I slide over one step, (4.8) divided by 40 and divided by 2, I still get that 0.6 out front. I end up with 1 minus e to the negative 40t squared plus W0. And again, to kind of make things fit, I kind of left out some steps because I know what it's going to look like in the end. But yeah, if you plug in 0 here, you get 1 minus 1, so you get 0 for that expression. So it really is just the t expression there. And I've still got my W0, which I kind of forgot up here. But the rest of that works its way down through. The other thing that would also help in this is at some point I needed to find what W0 was. And again, this is very sloppy, but I want to leave things on the same page. So for our specific example, if I just think about the fact that W0 is I0 times V of 0, then W0 is, when I put 0 into this expression, I get 0.024. When I put 0 into this expression, e to the 0, 1 minus 1 is 0. So the voltage is actually 0 at 0. So my initial work does end up going out to 0. So I can actually say that my final expression for our example is that the energy stored is 0.06 times 1 minus e to the negative 40t, that entire quantity squared. So sorry for a lot of mess there, which will be very tough to read if you didn't follow along as I was doing it. But I thought it would be good to show this side by side instead of moving to a new sheet. So again, key points here. We have an expression for stored energy as a function of current, the voltage, and the initial. And then we also learned a little bit about how to use the chain rule to use an expression. If you have the derivative of an expression beside it, then you can treat it like you would the power rule. And that'll become useful for many other things besides just the power rule when we get into things like cosine and sine. If we have the expression outside, we can actually use those.